Yep. Okay, I have a great pleasure to introduce Amir Algom from University of Haifa Orani as our third speaker, and his title is Fourier decay for self-similar measures. So please.
Thank you, Antti, for the introduction, and thank the organizers for inviting me and for this lovely event. So in this talk, we'll discuss actually many people's works, but my own work that I'll discuss is joint with Federico Rodriguez-Hertz and Jiren Wang. So I worked with them when I was at Penn State. Okay, so so the plan for this talk is the following. We will discuss the Fourier transform. Hopefully, I'll only say things you already know. Then we'll turn to some basic examples, and then we will also mention Bernoulli convolutions that you would think are simple examples of really they are already quite complicated. Then I will state some of the state-of-the-art results on self-similar measures. There are a lot of results, even for self-similar, but then if you move to smooth IFSs, there are even more results. So I'll focus on that case, and I'll say, well, we'll talk about that then. I will discuss two problems that I find are major open problems in this setting. So I say this is my opinion, but I think many people share this opinion. And finally, I'll discuss the problem of decay for smooth images when the IFS has non-cyclic contractions. I'll say what that means when that becomes relevant. Okay, so what is the Fourier transform? We fix a Borel probability measure on R and a frequency Q. So let me just remark that in principle, all my measures in this talk are probability measures on R with the one exception, which is the Lebesgue measure. So the Fourier transform of nu at frequency Q is given by the usual formula. What's slightly unusual here is my notation. So the reason I denote it this way is because later we will scale things, we'll scale a measure, and it's convenient to have something other than they have, because then in LaTeX it becomes a mess. Okay, so there are two basic problems that I will discuss in this talk. There are many problems you could talk about for the Fourier transform. So the problems that interest me are, does the Fourier transform decay at all? Is there some decay? So this is called the Reichmann property. This is already known to have several implications on the measure, on the support. That's one thing. So again, decaying measures, what we call, so they are called Reichmann. And the second problem is, if they are Reichmann, can you indicate a rate of decay? So this is also a very interesting problem. By the way, these two problems are not the major open problems that I mentioned before. Now, if you can indicate a rate of decay, there are many interesting things you can say. For example, so there's a classical result of Davenport, Erdős, and de Vogt that says that if you can establish log decay, then that's enough to deduce that almost every number in the support is normal to all integer bases. Now, for a very long time, this was virtually the only method of doing this. Later, there was the method that Alexei mentioned that Kaufman and Schmelken developed that completely avoids Fourier analysis and does this using establishes pointwise normality using the scenery flow. So there's that. Then a more recent result of Pablo says that if you have polynomial decay, then you have very strong things. For example, if you convolve your measure with a measure with dimension 1, that would yield an absolutely continuous measure. And so it's typically very hard to deduce that a measure is absolutely continuous. But if you have polynomial decay, then you have something. So here lambda stands for the Lebesgue measure on R. So there's that. Okay, so I promised you some basic examples. So let's do that. So my first basic example is the Riemann-Lebesgue lemma, which says simply that absolute continuity implies the Reichmann property. So if you're absolutely continuous, you have some decay. I don't know how much decay, but some decay. Then there's the other end of the spectrum, which is Wiener's lemma. And this ensures that it says that if you have an atom, then the measure is not Eichmann. But everything in between, I don't think there's any general method of doing things. So let's look at one ad hoc example. So suppose we consider the middle thirds, the Cantor-Lebesgue measure on a middle thirds counter set. So if you don't want to read the whole formula, just Cantor-Lebesgue measure. So this measure is well known to be singular and non-atomic. And so neither one or two hold here. And so you need a new idea. And that idea is the following. So for every Fourier coefficient for every integer, the Fourier coefficient at times m is equal to the Fourier coefficient at times 3m. This is just due to times 3 invariance. And from here, it follows that the measure is not Eichmann, simply because being singular means they can find one of these guys, which is non-zero, and then you have a cookbook of going to infinity along a non-decaying sequence. So there is a moral to this story, and the moral is that arithmetic structure can cause you not to be decaying, can cause the measure to fail the Eichmann property. And it's also natural to ask whether or not this is the only type of obstruction you can have. And I would say again, morally, yes, but not exactly. And this brings us to the topic of Bernoulli convolutions. So what are Bernoulli convolutions? I think hopefully everyone knows, but still, we fix the parameter r in the interval, and we consider the measures nu sub r defined this way. The plus minus here are unbiased. So this is an unbiased Bernoulli convolution. And we consider the family of all Bernoulli convolutions. And I would say one of the most fundamental questions in fractal geometry is, so can you find parameters? So for which parameters in the interesting regime do you have absolute continuity? Let me just remark, so I think this question is due to Kirshner and Wintner from around the 1930s. I believe, so it is my understanding that at the time, people had the following reasoning. So for r equals 1/2, you'll get a measure that's equivalent to the Lebesgue measure on an interval. And they thought due to overlapping, if you take r larger than that, you should still have this absolute continuity. But this reasoning turned out to be false in a very famous paper of Erdős. So Erdős proved that if the guy is piezo, then the measure is never Eichmann, and consequently by Riemann-Lebesgue, it is not absolutely continuous. By the way, I believe these are the only known examples in this regime where the measure is known to be singular. Now, I'm sure almost everyone here, probably everyone knows how to prove this theorem, and yet since this is relevant for our talk, let me go over the idea of proof. So how did Erdős do this? So there are two important things coming into the picture. One is convolution structure. So since we know that so the measure is an infinite convolution, you have this very nice formula for the Fourier transform. And this really reduces a problem that's a priori analytic into, so introduces algebra and number theory into the picture. So basically the idea is if you want to get decay, you want this guy to be bounded away from the integers. And if you want to, if you want decay, and if you don't want decay, you want it to be very close to the integers. And this was roughly Erdős's idea, namely, so the piezo property can then be used to show that powers of r approximate the integers in an exponentially fast way. And so if the parameter is piezo, then you have this property, and you can use that to make this whole guy bounded below. How so? So this can be used to show that there exists a uniform constant that only depends on r, such that for all integers, so here by integers I mean mostly negative integers, if you consider the Fourier transform at negative powers, so okay, at powers of r, again, if you think about negative powers of r, then this is bounded below by a guy that only depends on r, this infinite product. So again, so Erdős's idea was you plug in instead of q some power of r, and then you absorb it into this whole thing. And that could be, with some algebra, that can be used to bound this away from 0. And let me just also comment that a few years later, Salem completed the picture in terms of the Reichmann property, showing that if the measure is not Reichmann, then the guy has to be piezo. So the only non-decaying guys are piezo. Let me also comment that for a very long time, the research has been focused on ideas similar to this. So you look at this infinite product and you use algebraic ideas to either bound it or non-bounded. There's the Erdős-Kahn argument that I'll mention later that also uses some kind of an idea like this. Anyway, this brings us to the topic of self-similar measures that were actually defined in Dejeune's talk, but still, just for the record, so we fix a family of non-singular real affine contractions, and we fix weights. And then by Hutchinson, there exists a unique compact set, non-empty, that is the union of its contracted copies. And there exists a unique probability measure that is stationary in this sense. So note that the set does not depend on the weights, but the measure does. So nu is called a self-similar measure. And for example, Bernoulli convolutions are self-similar measures with this IFS and these weights. One final thing that I want to define is what I mean by conjugate. So an IFS is conjugate to self-similar if you can find, if there's a C2 map such that up to changing coordinates according to H, it is self-similar. So this is the exact definition. So by the way, H can be affine for these, and it will be affine in a moment. Okay, so now this brings me to the topic of some recent highlights on Fourier decay for self-similar measures. So in this part, what I'll do is we'll fix an IFS. Contraction ratios are RIs, translations are TI, nu is my measure. It's always assumed to be non-atomic. One thing that turns out to be relevant is, so we say that R and T are dependent if the ratio of the logs is rational. Otherwise, I'll say that they are independent. Okay, so the first result that I want to mention was a breakthrough by Lee and Solston from, okay, so this is the year of publication. The paper actually appeared, I think, in 2019, but it was published in 2021. So if you have independent contractions, then all self-similar measures, as long as they're non-atomic, they are Eichmann. So yeah, I sometimes refer to this as non-cyclic or aperiodic IFSs. And furthermore, they can indicate some rate of decay if there exists I and J such that this ratio is a Diophantine number. Now, I didn't want to define what a Diophantine number is. Let me just say what it is. By Diophantine number, I mean that if you dilate it by large guys, it stays away from the integer lattice in some quantitative way. That is a Diophantine number. So if this ratio is Diophantine, then they obtained logarithmic rate of decay. Let me just say that, as you'll see here, there are many results with logarithmic rates of decay, and one of my goals here is to explain why logarithmic. Why is it that logarithmic rates of decay arise in this problem? Okay, so that's one thing. Then, so with Federico and Giren, we give another proof of this result, and we also extended the effective result, namely, we proved that assuming the vector of contractions is the affine log contractions. So, okay, the affine vector is a little bit different than the affine number in the sense that for all large enough dilations, you can find one of the entries in the vector such that if you dilate it, it will stay away from the integers in some controlled way. However, it is possible that all entries are Liouville and all ratios are Liouville. So that such guys, actually there are many such guys, and this was proved by Moser in the 1990s in the context of KAM theory. Anyway, that's well known. So if this vector is Diophantine, then the measure has logarithmic Fourier decay. Okay, so now let's talk about the cyclic case. So what about in the case when there is dependence? So this was treated by Bermond and then Rappaport in higher dimensions. So if the measure is not Reichmann, then, so okay, we know that contractions have to be cyclic because this is the Solston, but then what Bermond proved is that actually all the guys are powers of the same guy, and that guy is Piso. So this is a very strong analog of the Erdős result. Furthermore, the IFS is a finely conjugate to an IFS that has all of its translations in the corresponding extension field. So this is actually an even stronger result, an even stronger analog of the Erdős theorem for Bernoulli Convolutions. So let me just say that this result is due to Bremont, and Rappaport completely resolved the Reichmann property in higher dimensions as well, but that's a little bit beyond the scope of this talk. Then there's the question of effective rates in the cyclic case. So this was treated in greater generality, first by Buffet of Solomiak, then Gao and Ma, and recently by Value and Yu. So they proved that in the Bremont situation, if the R is an algebraic integer that's not Pizot or Salem, then you have log decay. So the history is Buffet of Solomiak in a slightly different context. So, okay, it was a byproduct of another problem, but they obtained this result for Bernoulli convolutions. Gao and Ma did it for homogeneous guys, for all contractions equal, and Value and Yu proved this result as stated. Actually, Value and Yu proved something much more general, but this is actually only a consequence of their method. Okay, and let me just say, I couldn't fit everything here, but there are early results, for example, by Watanabe and Day about logarithmic decay for certain balloons. But I just couldn't fit it inside. So there's that. Okay, now let's talk about the first major problem that I want to mention, which is polynomial decay for self-similar guys. So recall that nu sub r is my notation for Bernoulli convolutions. And then a famous result of Erdős, and then in greater generality due to Kaufman, says that outside of a zero-dimensional set of exceptions, Bernoulli convolutions have polynomial Fourier decay. So by polynomial Fourier decay, I mean exactly this thing. So Erdős did this for prove that exists E with the Lebesgue measure 0, and then Kaufman noted that actually this works. The same argument will give you dimension 0. And very recently, Solomiak showed that this actually holds for all self-similar measures, namely, outside of a zero-dimensional set of exceptions, as long as your measure is non-atomic, it will have polynomial decay. And this raises a very natural question, which is, which specific self-similar measures have polynomial decay? So while we see that this is a very generic, I'm not sure if generic, but very general property, very few examples are known. Virtually the only examples known to me are in a very nice paper of Dei Feng and Yang Wang, so not Jiren Wang, my collaborator. This is another Wang. So they proved that for Garcia parameters, the Bernoulli convolution nu sub r has polynomial Fourier decay. So actually, I think the result is a little bit more general, but I think this is the main class of examples that we produce. So do note that Garcia parameters are those parameters that Garcia in the 60s established absolute continuity for corresponding to the Bernoulli convolution. Yet Garcia does not talk about the density and does not talk about and does not establish decay. So this is what they did, and I think so. Actually, this is a good form to raise this problem. I'm not sure. I'm not aware of any other result in this direction, or like specific polynomial decay for self-similar guys, not generic, specific IFSs. Okay. On the other hand, so I mean, you can think that maybe the Pizot property is the only issue that can arise, but that's not the case. And this was shown by Kahan, and then also in the same paper of Dei Feng and Wang. So if the guy is Salem, then you do not have polynomial Fourier decay. And let me just mention that the question of polynomial Fourier decay for Bernoulli convolutions is especially important because of its relations with the absolute continuity problem. Okay, so that's about polynomial Fourier decay. Now let's talk about a second major open problem, at least in my opinion, which is Kaufman's theorem. So Kaufman's theorem is the following result. So we fix a self-similar measure, and we assume all the contractions are equal, so it's homogeneous. So if all contraction ratios are equal, and you push the measure using a generally nonlinear map, so with this condition, then the push forward will have polynomial Fourier decay. So this is really, for me, this is a remarkable result. So the nu does not have to have decay, but changing coordinates in a smooth way will yield polynomial, will lead optimal Fourier decay, will lead to optimal Fourier decay. So the history behind this is Kaufman proved this in the 80s, yet it was, I think only very few people knew about this result. It was in some conference proceedings. And So, okay, this is only my conjecture, but I think this was rediscovered by Muskera-Shmirkin around the time when the Ochman-Shmirkin paper was written for this point-wise normality. This is only, by the way, my conjecture. I don't know this for sure. So then they became aware that this result existed because it implies also point-wise normality. And then Muskera-Shmirkin, let's see, there's a comment. Oh, okay, yeah. So Pablo is commenting that he learned about this from Boris, from Soromek. So, okay. Yeah, okay, so my conjecture is wrong. Many of my conjectures are wrong. So at any rate, Muskera-Shmirkin did this for all homogeneous IFSs. Actually, they also give some quantitative estimates on the rate of decay. And this raises a natural open problem, which is this true for all subsimilar measures? So if you do a smooth change of coordinates, if you push the measure using a smooth map, is the measure Reichmann, and can you indicate a rate of decay? So with Federico and Jiren, we did make some progress on this problem. So we proved that in the non-cyclic case or aperiodic case, the push is always Reichmann. And furthermore, we proved that if the vector of contractions, log contractions is Einstein, then you have log decay. So, and actually, my last two slides this talk are dedicated to the proof of result. And also, as I said, I owe you an explanation about why modern methods only yield logarithmic decay. So, but just to summarize this discussion, so the Reichmann question regarding this Kaufman theorem problem is open in the cyclic yet non-homogeneous case. There's that. And then the question of polynomial decay is open in all non-homogeneous cases. Yeah, so there's that. Okay, so then let me end this talk with a brief discussion of our method with Federico and Jiren. So I need one slide of preliminaries. So, okay, and do forgive me for lying. I'll be lying a lot in this sketch, but I just want to convey the main ideas. So we fix a conjugate to linear, conjugate subsimilar IFS of this kind. K is my attractor. I fix a correlative vector P for my measure. And we do note that the push forward measure in this situation will be self-conformal measure for the C2 IFS psi. Actually, this whole thing works for all C2 IFSs, but I didn't want to introduce more notation, state things that way. So from here on, you can just assume psi is C2, and that will be fine. Okay. So now we introduce a random walk. We fix a point in K, a reference point, and for every multi-word, so every word of length M, we define a random variable Sm of I. Actually, here it's not a random variable, it's just a map. Sm of I is log of the corresponding fraction. So the idea is that the Sm, when you go over all words and all M's, you see the multi-scale structure of the set. Yeah, but only the scales, right? So this has nothing to do with the translations. But I do want to point out that Sm is exploding. Sm has to go to infinity due to contraction. And so we can define a stopping time. So a stopping time, so given a positive K and some omega, we have tau K omega, which is the first time that you escape beyond K. So there's that. And so do know that this has to happen. And now we have an important random variable for our needs. So f tau K of omega is the value of the random walk at the stopping time. And note that this will give us a real random variable on the interval k plus 1. So the k will be moving. So note that obviously this lives on something that's larger than k, that this is k plus 1. It's actually k plus d for some uniform d, but let's assume it's 1. Why not? And this is with respect to the product measure on the product space. So just to comment again, the moral here is Sm is going on scales inside the multi-scale structure of the set. And what's important for us is that you can show that Sm is really driven by a cocycle, and that allows one to introduce the theory of Benoit-Quint into the picture. This was our innovation in this respect. And now let me talk about how using SM you can decay. So again, I'll be lying a lot. This is just a very rough outline, but it's already late and probably all of you are tired by now. So we fix a probability vector P as above. We fix our push measure, which is stationary. And let me also introduce one final piece of notation. So MS is the scaling map, and K will be roughly the log of the frequency. So actually, the dependence on K on the frequency is very important, but I won't have time to go into how we do that. So there are 3 steps to our method. The first step is linearization. So we bound the Fourier transform of nu using an integral against scaled copies of nu against this random walk. This is where it appears. And note that the measure is this infinite product measure. So actually, okay, 2 remarks. First of all, this uses self-conformality since tau is stopping time. Actually, in the actual papers, tau is not a stopping time, and that introduces more problems. But we want to do things symbolically. And if we want to do things symbolically, tau is no longer a stopping time, but never mind how we get around that. And there's also an error term to be introduced here, but I didn't want to. Okay, so now we have this integral, and now the question arises on distribution of this random variable. And this is really the gist of our method, which is equidistribution. So we show that S tau k is, well, it becomes smooth. So it's absolutely continuous with respect to the corresponding Lebesgue measure with a uniform density. So C stands for uniform density. So C does not depend on K. This is a critical thing. Up to a error. How small the error is. So I'll get back to the issue of this error term, which is actually very important. And if you believe this, so first of all, this uses the central local limit theorems of Bernoulli, which are certain equidistribution theorems that they proved for random walks, but we were able to bring this into our setting. There's that. And if you believe this, then you get a new upper bound, which is, so using this result, you get a bona fide oscillator integral. So then you bound your Fourier transform against an oscillator integral, which is already, so doing this is very common, somewhat common idea in fractal geometry. You want to understand something, so you think there's an integral against things you do understand, and then you work. And so there are ways of estimating integrals of this kind. So note that what this means is that we bound the Fourier transform nu against the Fourier transform, so the Fourier transform of measures scaled by this random guy, but the random guy is going against Lebesgue, not against this discrete measure. And again, there will be an error here. I didn't put that there, but there will be an error and you have to control that. That's a pain. Okay, and the final step is using high oscillations. You can show that this thing is actually small in K, but small in K is also small in Q. The method that we use to bound this thing is from a recent paper of Mike about Hooft's theorem. Actually, this whole method is inspired by this paper of Kaufman on a new proof of Hooft's equidistribution theorem. Okay, so now let me end this talk with 2 comments. So my first comment is effective rates. So our method essentially depends on how fast is this equidistribution happening. Now, and this brings us to the topic of why logarithmic decay. So note that suppose now the IFS is subsimilar. There's no loss of generality in that. Then the Sn can only, so the Sn lives on polynomial in many points, right? So if you have a distribution on polynomial in many points, it cannot be, so the error term for that and the corresponding Lebesgue measure cannot be better than polynomial, cannot be exponential. And since the rate of, since the k is log of q, log of a polynomial would be, well, so if you get polynomial decay, since because of the relation between k and q, you'll only get logarithmic decay in the frequency. That's the issue. So roughly speaking, the decay for Q will be log in the error term here in the equidistribution. So for our method, and I think also for the Lee-Solston method, this explains the logarithmic decay. So if you use equidistribution results like this is roughly speaking the best you can get. If you introduce smoothness into the picture, then you may expect sometimes this guy will be exponential, which will give you polynomial rates. We are working on that right now. One final remark is that the good thing about so again, I'll end this on a Parash-Barani note. So the good thing about our method is that it works equally well for self-similar and self-conformal measures, in the sense that the same argument works for whether or not the IFS is smooth or affine, which is nice because it's a uniform proof. It's a unified proof. The bad thing about our method is that it works equally well for smooth and self-similar IFSs. And the moral reason is that when you have smoothness in the picture, say in the line of Kaufman's theorem, you expect better bounds on the decay rate. And this is not something that our method currently shows, but we are working on that. Okay, I think I'll stop here. Thank you for your time.